Um, so welcome to the evening edition of the Toronto Data Workshop. Our guest is Dr. Emi Tanaka, who is an assistant professor of statistics at Monash University. And her primary interest is developing impactful statistical methods and tools that are actually used by practitioners. So that's a fairly rare research interest as far as these things go. So she's very interested in data visualization, mixed models, and especially experimental design, which is going to be the focus of her talk today. She's the president of the Statistical Society of Australia, Victorian branch, and has won just a variety of awards, including a Distinguished Presenters Award for a wide range of our workshops. So it's a pleasure to have a guest from my homeland, Australia. Thank you very much for joining us, Emi.
Thank you very much, Rohan, for the invitation to talk. And thanks to everyone for joining, because I know this is outside of your regular seminar times, having been at Thursday, 5 p.m. To accommodate my time zone. So today I'm going to be talking a lot about the anthology of experimental designs. And it's going to be semi-interactive. So during the talk, feel free to just unmute or even put in chat what you think as I ask some questions to you. So I'm going to begin with, because we all a lot on Zoom, or at least we were quite a lot on Zoom. So I thought maybe people have shorter attention spans. So I thought I will begin with takeaway messages from the very beginning. So at least if you can't bear to listen to me all the way through, you've gotten the main messages right at the beginning. So takeaway message one. I'm going to be talking about the package I'm developing. It's an experimental R package. It's getting close to really full completion. Well, the first official release. And that package is called Edible. And it's planned to actually do planning, design, and simulation of experiments. Now, Edible stands for Experimental Design Table. Or for those people who are familiar, with the tidyverse, it's experiment design table. And it's aimed to provide experimental design in table format. You can find actually the code in the link, the GitHub link that you see in the slides. And just a fun fact, it is really commonly misspelled as edible with one B, because perhaps it was because of autocorrect. The next one is the Degas. This is another package I've been working on. This is a lot more premature than Edible, but it's a bit of a companion package. And this one is to actually easily visualize edible experiment design. And Degas actually alludes to the fact that the D and E in that package name stands for design of experiments, and the double G that you see in the middle actually means stands for ggplot. So the ultimate aim for Degas is to provide a ggplot objects, which is actually going to be representing your experiment design. And you can find the code for this in the GitHub link that you see there, github.com/emitanaka/Degas. Now, Degas, that's with double Gs. It is a play on the word, on the verb degust, which is to, if you go for degustation menu, it is about savoring and appreciating really that food. It's kind of similar to that in a sense that when you do this visualization, you're fully savoring and appreciating the design that you have just created. And the third takeaway message is about the edible system as well. And the way that I have actually designed this software is to really reframe the way you think and construct experimental designs. And I haven't got the paper out, which is my to-do list this year. But it really is, from my point of view, very significantly different to really the standard approach, which often can be very recipe driven. What I'm trying to do is to get more into the fundamentals and try to get users to really think about the experimental design. And this whole system I refer to as the grammar of experimental designs. For those people who might be familiar with things like ggplot2, that is using what's called the layered grammar graphics, which was an extension on Wilkinson's work, the grammar graphics. And the layered grammar graphics is, as many of you may know, written by Hadley Wickham. So it's kind of like an analogy of that, where the grammar graphics really was the one that actually helped you to kind of think of drawing plots by thinking about how the variables in the data relate to the aesthetic components in the plot, right? The editable approach is going to be somewhat similar. And the whole thing is not really supposed to be language specific. It's supposed to give you a framework and the way, like, you construct designs. It so happens that, I'm more familiar with R, so I am implemented as an R package called Editable. So at the bottom of this, I try to really develop this more kind of like a principles, standard kind of framework of how you think about constructing experimental designs. And then on top of that, like also aiding it in terms of planning as well. So I am writing a book called The Grammar of Experimental Designs, and this is actually one of the only things that's public in terms of the writing. My other papers are actually still just lives on my Dropbox at the moment alone, but hopefully that will get submitted sometime this year. So if you want to see the work in progress book, you can look at the link emitanaka.org/editable-book. So those are the 3 takeaway messages. And, if anything you get interested, you can look up at those resources. And at the very end of this presentation, I will give you like a link to the slides itself as well. So it is getting recorded, but also like if you feel like you want the slides itself as well, don't worry, like I will give you the link at the very end. Okay, so let me start. And let me start with a series of experimental design short stories. These are stories that I've grabbed from 3 different books. So the books references you can see there. So, and I'm going to butcher the name, but Giersberg and Gumpertz, 2004, Planning, Construction, and Statistical Analysis of Comparative Experiments is the first one I'm going to show. Then I'm going to show Rosemary Bailey's design, one of them, and John Lawson's experiment design as a 3rd story. So, first story, The Folklore of Fervent Field Experiments. Now, bear in mind, it's going to be a bit descriptive. And so as I'm reading it, I want you to kind of think about what is the experiment structure, and like how would you think about constructing experimental design? So consider a field experiment in agriculture where plots are laid out as 6 rows by 8 columns. And these rows and columns are also referred to as strip. There are 4 modes of seedbed preparation and 3 crop varieties that are the interest of the researcher. The mode of seedbed preparation is assigned randomly to the whole columns, and the crop variety is assigned randomly to the whole row. This experimental design is called a strip plot design. Now, my question to you here is that what sort of units are we looking at in this experiment? And since it's a comparative experiment, there will be treatments as well. What is a treatment? And while you're at it, how many do you have? Like how many treatments are there and how many units do you have? Mike was being nominated. The seedbed prep. Yep. So that seems like a factor in this experiment. What kind of factor is it? Like, is that like the treatment of interest, or is that like the units? Is that observational unit, experimental unit? And maybe I should have started off asking whether you were familiar with some of these experimental design terms. So let's start off with treatments. What's the researcher interested in comparing? What kind of experimental conditions are we comparing? Yeah, 48 units and 12 treatments. I think you are right. But treatment-wise, so what is it? So here we're becoming, usually what happens with experiments when you specify them in the software, it tends to get stripped away from the context. And then you kind of like get out what the experimental unit is. You may get out the treatments, but then what exactly was a treatment? What exactly was that experimental unit? Yep, so go ahead. How different crops grow given different seed beds. Okay. So I'm gonna start highlighting certain parts. So units that are involved. So these are like, it could be physical, but sometimes they might not be physical, but these are something like required in your experiment in order for you to do the testing, right? That's something that you're applying the experimental condition on. So a couple of things that tell me what the units are that here we got 6 rows by 8 columns. That's describing something physical. It's to do with the field experiment itself. So there's a plot out there of land that's laid out in this manner. And then what happens is that, so 6 by 8, and then so each component is going to correspond to a plot, which you might actually need to know a little bit of the domain knowledge to understand the full context. Then there's this 4 modes of seedbed preparation and 3 crop varieties that you're interested in. So this is what the researcher is interested in. The mode of seed preparation is assigned randomly to the whole columns. So now imagine that you got this rectangular region, right? Divided up by 6 by 8. And then what happens is that the seedbed preparation is basically assigned randomly according to the different columns. Crop variety assigned randomly to the whole row. Okay, so the design to specify this using the editable system is given by the code here. And let me go step by step. First, load the library editable. I'm going to initiate the design, and then what you give here is just the name of the experiment. So I'm just going to call it strip plot experiment. The units. So I've got 6 rows. I've got 8 columns. And then the plot is actually like a cross of the row and column. So the row and column index a particular plot itself. Then I've got the treatments, right? It says that we've got 4 modes of seedbed preparation, and then we've got 3 varieties. So variety equals to 3. Now, in terms of the allotment, or some people call it assignment, allocation, mapping, what happens is that the seedbed treatment is getting applied to the column, right? And the variety is getting applied to the row. And then what I'm doing here is a randomization. So I'm just going to do a random order. You can do things like systematic or any other kind of ordering. And I'm just feeding a seed number so that it is reproducible. And when you get to that point, if you're done specifying all the steps and the components, what happens is that you can serve the table. So this is a moment when you say, I'm ready, I'm done, get me the table now. So the process that's going under the hood, which is what I'm calling the grammar experimental design, is that you can have intermediate constructs of experimental design. And to me, this is part of the biggest innovation that I offered, in that when people think experiment design and specifying the software, it kind of goes from 0 to like 100. Like you basically, have to go from scratch to somehow having the whole experiment design. But actually, when you're thinking about your experimental structure, it kind of helps to think it piece by piece. And so you build it up. So under the hood, what's happening in the system is that it's creating a graph, a network, and it's all the factors are represented as a node. And then, so there's two graphs that are represented under the hood. One that's level showing under the factor level. So it's a higher order view. And the lower order view is where you got the levels. So that's actually saying, oh, you got it's got six rows. So, create 6 nodes here. And then you got 8 relationships, like what's getting allocated to what's nested in under which particular unit, which units are crossed together. These are represented as edges essentially in that network. So it's not a full table at that point. But what happens is that the user builds this graph under the hood. And when it gets to the very end, when you're ready, you can serve that. And the table gets served when what happens is that it can be all the level nodes that you have can be reconciled to a single observational unit. And so that's what the serve table does. We see if you can reconcile it, and then if it works out, it will print out that a randomized design for you. So that's what I get here. And at this point, this could be something that you take and implement. But as an extension, what I did was started developing the Degas package. And the idea of the Degas package is to try to make the visualization of experiment design as easy as possible. Now, as a user, you would have, made it really that code that you just saw is quite verbose. You put in a lot of work specifying the units, specifying the relationship between the units. And what happens is that Degas is leveraging off what's already there. So you specified all the structure. Let's try to come up with an automatic way of visualizing your experiment design in a quick fashion. And the idea behind this is so that it aids in communication as well. So if you are consulting and you're talking to your domain expert, you could actually just quickly say, okay, is this right? Is this what you want for experiment? Or if you are designing it yourself, you can also quickly check it as well. And so there are no issues. So this really the main function with Degas package is the function autoplot, and then you pass in your design, the editable design that you constructed, and the result is a ggplot object. So what happens here is that because it's a ggplot object, any functions that you can do to modify ggplot object can be used. So the latter function where I've got the theme part, that is to do with the ggplot functions, right? It's not to do with the Degas. So what happens is that it's got this ability to leverage off existing systems. So the user doesn't have to learn a whole new visualization system. I'm using existing very popular system, and essentially you can modify the look of it based on that. And so you get the following experiment out, and you can see here, and this is very much work in progress. So I'm still kind of thinking about how it should be in the end result. But you can see there's 2 factors for the treatment, the seedbed and the variety. And what happens here is that you've got the circles where the circles correspond to the plot. And then what happens is that you can see the outer color of the circles actually show you what seed bed it's been allocated to. And remember how seed bed was allocated to the columns? So it's randomly allocated. So the first column, the whole first column strip has been allocated seed bed number 4. Like the second column has been allocated seed bed number 2. And then we got seed bed number 4 again in column 3 and so forth. In terms of the row, what happens is that this is the one that the variety was allocated to. So you can see the, like, you know, row number 1, you got the variety number 3 getting allocated in that one. So it's a factorial experimental structure. And then what happens is that the way its allocation it works is that it's based on the row and column itself. Okay. So that's the plot. And what I'm gonna do is I'm gonna go back to the description, but let's say now, okay, you realize I've done my strip plot design, but you realize there might be an issue. In particular, what happens is that notice here the seed bed number 4 appears in column 1 and 3. And then column 6 and 7, like consecutively, what happens is that seed bed number 3 is getting applied. So what happens with this in agriculture experiments, there could be like a concern to do with this fertility gradient, where one side of the block might actually have like more similar fertility, right? So what happens is that I'm kind of confounding, like maybe perhaps an extraneous variable with actually the treatment. So it's going to be hard to tell whether this particular crop actually grows well, it's to do with the treatment, or whether it's to do with these extraneous factors. So I might actually think about modifying it so that there are what's called blocks in the experiment. So I'm gonna say, okay, fertility gradients may be suspected. So I'm going to start putting the strips as sort of like sets together. So instead of having so that consecutive treatments appear like on one side, I might create like 2 blocks. So I had like 8 columns together. So I might create a block with 4 columns each. And so sometimes blocking factors, you don't really have a choice, but in like things like this, where there's a continuous gradient, you can kind of like choose as a designer, like where the blocking sets might be. So that's what I'm gonna do. I'm going to now essentially create a block of 2, and then the column is now split. The 8 columns are now such that there are 4 in each blocks. So in total, I had 8, but then I've divided so that there's 2 lots of 4 columns instead. And so that's the code that you see here. Block equals to 2, and column is now nested in block with split across with 4 in each of the blocks. So the rest of the code is the same. That's the only part that I changed. And so what happens with Edible is that it notices that there is this nesting structure. And when there is this hierarchical structure, it kind of thinks that maybe perhaps when you allocate the treatments, you want to make sure that every treatment is spread out across the different levels of the hierarchy. So different blocks have all the treatments appearing. So it tried to do its best to spread the treatment across the different blocks. So the result is something like this, you see. So it's kind of like laid out still as 8 columns by 6 rows, but there's like a split now. So the columns are split according to like 4 columns. And notice here, because of this nesting structure, when Edible does the assignment of the treatment, it tries to really spread out the treatment so that it doesn't too many doesn't appear in the same block itself. Now you can choose to ignore this nesting. So there is an option in assignment treatments where you can remove that constraint and you can let it go wild if you want. So you might end up becoming like the previous one as before. So in this case, like what happens is that I made a decision as a developer that perhaps most of the time when the user means nested, more likely that they would want to have it balanced across the different levels of the top hierarchical factor. So you can see here, yeah, randomly the seedbed. In this case, it's really nice. You know, you got 4 columns, 4 seedbeds, so 1 each of the seedbed per block, essentially. You might also want to do the same for the rows. Here, what happens is that with the rows, I've got also the variety 1 appearing consecutively in row 4 and 5, and that might not be desirable. So you may wish to change that, and you certainly can do that. So I created 2 blocking factors now, block R for row, block C for the column, and I can break it up to 2. So with this one, what happens is that some designs are not supported at the moment for visualization, but you can go to the actual like ggplot code on the bottom, like the downstream. And I'm just showing here with the Degas, it's pretty much ggplot code, except for the geom unit node, which I created, which allows you to do certain ways of changing the shape of what your unit looks like. So here I'm demonstrating a unit where the outer unit is actually depicted as a circle, which is a default. And then the inner one, which shows a variety, is shaped like a square. You can change this. So for example, maybe it might make more sense to have like a case where the unit is depicted by an image that you supply. You can actually supply an image. And so your units are actually represented by whatever suits the context the best. So you might get an image of like a plant in this one and then put it in there. So this is sort of the idea like behind really editable. We are really trying to dissect that, and you know, like try to think like if you're trying to modify it, you shouldn't have to think about modifying like the whole function. You're only modifying parts of it, and so editable allows you to modify the parts that might be most relevant that you're tweaking, and then maybe the rest of the things are still the same, and in that sense you don't have to do a whole lot of work. Just like here, the only thing that I changed was the unit structure, so only the unit part really gets modified. Okay, so that's the first story. Before I go on to the second story, does anyone have like questions, or would you like any qualifications in case I wasn't clear? Yes, thumbs up if you're okay. Yeah, got some. All right, I'll go to the next one, and it's also going to be wordy. And
Emi, I think we might just have a question from Leo. Do you have the chat open or no? I could read
yes,
it out.
I have. Oh, I missed it. Yep, it's up here. What about incomplete design? Are they? Yes, incomplete designs do work. So in this case, it turned out to be really nice, but you can do incomplete designs. Unfortunately, I don't have an example in today's talk about it. What I might do is I can do live coding a bit later, and then I'll show you what happens in that case. One thing to note with the allocation of the treatments with editable is that it is somewhat naive. I tried to come up with like what might be sort of work in most scenarios. And so it does, when I checked, like it can do things like balancing complete block design. So that was good. But the problem is that sometimes like you might need a specific way of actually allocation. And so the approach that I've implemented by default might just not be suitable. And then, so if it's not, you might need to actually come up with your own. And that part is basically replacing the assigned treatments. So essentially you can slot your own thing by replacing the assigned treatments. The edible will already help you build the structure. If you can somehow understand how it communicates with each other, under the hood, you can like just write your own function for that part and replace it with whatever your favorite method is. I actually one that's implemented, that's another one. Yeah, maybe in the live coding, I can try to show that one if I remember how to do it. It is also the thing with edible is that I don't aim to be like the best, like the design to be always like the optimal. Because it's such a general package, it is really hard when if somebody works on a very specific case, they're more likely to be able to do better because they fine-tune it for that particular case. Whereas when you try to generalize it, it is actually a little hard to do that. And so there's a part of like, I'm hoping that, you know, once this foundation is built up, people can build up extensions of it. So if there are really specific cases that are quite common, somebody can build an extension based on this, and then you can just use that one in place. It is also the thing is that I think most research in experimental design is really about that assigned treatments part. There's not too much part that's been worked about in terms of trying to understand your experimental structure. And so this is the part that I think really significantly differs from the way that currently experimental designs are specified in many packages. Any more questions or? So let me go to the next one. And this could be very relatable for all of you, which is a horrifying tale of dirty laundry. A manufacturer of household appliances wants to find the best combination of wash temperature and drying temperature to produce unwrinkled cotton sheets at the end of the laundry session. He wants to compare 4 different wash temperatures and 3 different drying temperatures. He uses 8 similar washing machines and 6 similar dryers. First, 48 cotton sheets are randomly allocated to the washing machine, 6 per machine. The wash temperatures are randomly allocated to the washing machines so that 2 machines are run at each temperature. After the wash, the 6 sheets in each machine are randomly allocated to dryers, 1 per dryer. Then the drying temperatures are randomly allocated to the dryers so that 2 machines are run at each temperature. After the drying, all 48 sheets are scored by experts for how wrinkled they are. So, what are the units? What are the treatments? What do you see in terms of the allotment? And mind you, this one is difficult. Yes, unit is a cotton sheet. So certainly sheet is in there as a factor, and there are 48 levels for the sheet. Oh, I shouldn't have said that maybe. Oh. And keep in mind here, like it's quite long, right? With these experiment design descriptions each time. And I think a lot of the time when you read it, at least me, is that sometimes I don't actually understand when I read the experiment design description what exactly they mean. And so part of this writing up the code specification and being explicit about it is that we are trying to make sure we are on the same page. And somewhere essentially was edible, like it's kind of forcing you to say, okay, what is it that you are interested in? Which are the treatments? Which are the units? And how are they exactly related? Anyone know what the treatment is? Yep, treatment, wash temperature, drying temperature, 4x3, blocking factor, washing machine dryers. Okay, 8x6 cost. Okay, cool. Very good. So 4 different wash temperatures, 3 different drying temperatures. We got that washing machine, and we got 8 washing machines, 6 similar dryers, and then 48 cotton sheets. Wash temperatures randomly allocated to washing machine, and the drying temperatures, 6 sheets allocated to 1 per dryer, drying temperature randomly allocated dryers. 48 sheets are scored by the experts. So the code. So there's a few new functions, which this is one way. I'm going to show another way of specifying with editable, which you can still use the old functions. Okay, let me go through one by one. So treatments. We got 2 factors. Wash temperature, there's 4 of them. Dry temperature, there's 3 of them. Units. The washer, 8, dryer, 6, sheet, 48 of them. Now, there's a bit of a grouping structure going on, and that's what's happening in the next one, where I'm describing how the grouping is. So here what happens is that the sheet is getting allocated to the washer, right? And I'm still thinking about whether I should just have this other way around, actually, sheet to washer or washer to sheet. So I've got the bigger unit on the left-hand side, the smaller unit on the right-hand side. And so what's happening here is that the units are grouped so that the sheets are within the washer. And then for every sheet in the washer, it gets allocated to a particular dryer. So this is the part that describes that grouping structure. And so under the hood, it draws those edges and it says that, okay, these are going to be related in this way. This is a nesting structure you're going to, a cross structure that you're going to have. The allocation is going to be random. You can do systematic here, and there's other options as well. In terms of treatments, the wash temperature is allocated to a washer, the drying temperature to the dryer. And then the allocation here is random. And you want to have randomized designs if possible, so that your conclusions are more reliable. There's another one here that it talks about the intention of the what to do, measure. So the records here is that you want to take a score for every sheet that you wash and dry of how wrinkled they are. Serve table, and that's what I get in the very end. Now that's a little bit confusing maybe when you look at it. So let's look at the visualization of it. And here it is. And so the visualization here, essentially what happens is that the washer gets allocated a particular washing temperature, right? So wash temperature. And then so you can see there's a particular, in this direction, there's a particular wash temperature. I think this is the number 4. And then this is also number 4. So washer 1 and washer 8 gets allocated the wash temperature, number 3 actually, wash temperature 3. So this makes sense, right? That's what we would have expected, and that's what we specified as well in the design. And likewise, when it comes to the dryer, you can see that with the dryer, they get allocated one particular type of temperature. The washing machine takes like 6 sheets in, and then for every washing machine, it takes each one of them to a particular dryer. So it is that it's got that cross structure, as Leo has pointed out. And in fact, this is actually a strip plot design, if you notice, very similar to what we saw before, but we didn't call it a strip plot design. Didn't mention any names in it, because once you use like named experiment design, it takes out so much of your ability to understand what's happening under the hood. Now, the other thing that I didn't mention was that when you do the set treatments and set units, notice the names are never fixed. You can call it whatever you want. And the important part here is that unlike some packages which has a very fixed name, here I'm allowing you the flexibility of calling it as you see fit so that you can get the context directly. So when you get this 48, you know directly this is related with sheets. And I think this helps where I don't have any scientific backing, but I think it's as a and your experimental design context. Okay, so yes, this is in fact a strip plot design. And because you know that it is now a strip plot design, perhaps that you visualized it, you could actually have specified it in another way, which is that just like before when we had strip plot, we could say we got 8 washers dryer, recognize that the sheet is a crust within washer and dryer, and essentially it becomes a simpler version of what you had before. But there's multiple ways of actually specifying the same design, and it's more aligned with the user's thinking, right? We're all different individuals, and the way that we think about things are different. So what you want the tool is to be able to cater for your mental mode, not to hinder it or conform to a particular way of specifying it. This is really trying to get to the fundamentals. You have specified the units, you have specified its grouping structure, and the way that you specify, while there is some constraint, it's trying not to constrain too much in a way to inhibit your thinking about your experimental design structure. The other part I want to get to is this set records. So I'll just go here and then see the score, and then basically here it just creates a column, and it's basically showing an intention to capture like the particular response here, and so it's got nothing measured there. And you might think, why bother? Like it's not needed for the generation of experimental design. It's all because the design part is already specified by just this part alone. This one is only needed later on when you record your response, and then later on you may use it for your analysis, right? So why? Well, and there's a part in Edible which I think it was quite different to other packages, which is to really specify your intention of what you're measuring. And also you can do things like simulations, and also set expectations of what the record might be. So records in Edible is really like variables that you intend to measure or capture or observe. So generally speaking, responses. You can set expectations. So you say what the plausible values are. You can simulate the records, and you can also export the data with data validation if you have set the expectations. Here's expect records. And what this says is that the score should be greater than or equal to 1, and then less than or equal to 10. So essentially between 1 to 10. If you get a score higher than that, then something might have gone wrong. If somebody's put a negative number, that's certainly off, and so forth. So this is actually trying to, again, like get you to realize what might be like the plausible values associated with your records that you're taking. And then you specify this. It is extra work, but you can use this data that you have encoded in the object downstream. So as an example, what happens is that I can simulate the record, and this is a bit of a naive simulation where I say the score is normally distributed with mean 3, standard deviation 4. Now, what happens here is that because you have set an expectation before, and then with this particular naive distribution you have specified, you can get a number that is outside of 1 to 10. And so when it is outside of 1 to 10, it censors it. And by default, it's as censored as a missing value, but you can censor it to something else, 0 or whatever else that is right. So like you can use it for like simulation to make sure that values are in your expected range. The other one is exporting the data with data validation. So if I go to the coding part and then I set an expectation, so at this point you don't really see anything. You just get an output, right? I'm gonna export this. So export design, and then this is laundry experiment. So laundry. Okay, so it's been written. And now I'm going to open this laundry file. So open up here. It gets the data here. And then you got this score sheet, right? Which I don't know if you can see. How do I change the size? Zoom. 100%. Okay, so you got this. And here the score's been specified to be between 1 to 10, right? Let's say that the technician tries to enter the data and they make a mistake. And then, they enter maybe 200, 299. And then it will tell you, no, you've got a wrong thing. The data validation doesn't work here. So this is one way. And actually, I see this quite important because what happens is that, as we know, when we do analysis, if your data is garbage, it doesn't matter how fancy your analysis is, you can't get anything out of it. So I kind of see this as a way of actually getting more value from your experimental data. It's one way to propagate like better value from your information, but ensuring that the data is got some kind of like, it tries to help prevent you from putting in like implausible values. You can do things like, so that was a numerical value. Let's see if I remember this. So you can do factor, and let's do it level 1 to 10. I'm gonna call it laundry 2. I hope this works. Laundry 2. Let's see. And then it's a drop-down menu. So if it's a factor, you can essentially, select within that range. So I think this is basically leveraging off. Again, export design is a function that's within Editable. You might have your own specialty software. In medical research, things like VetCap are, quite widely used. It's a matter of somebody writing it. All the data is encoded in the object itself. So if you can like extend that, basically you can implement it so that it's got that like data validations as needed by the software that you are using commonly. There's more features, and I won't get a chance to talk all about it, although I'm happy to take questions afterwards. But the idea is not for me to do everything as well. Like idea is that if people who work in experiment design can also get on board, then this I think will help it so that we all have like a certain standard approach to do it. And instead of us all reinventing the wheel each time, we are actually leveraging off other people's work as well, and concentrating on what we do best, which a lot of for experimental design researchers, they tend to be the assignment of the treatment to the units. And certainly I think a lot more people are better than me, and my approach is very naive actually. Okay, I actually have one more story, but then I think I'm running out of time and this one is too wordy. So I might actually leave it there. And just show you the code. So this is like the cookie recipe. and just come to the very end and just say thanks for listening. I hope that you kind of got the feel that a lot of with these experimental design stories that I'm trying to get to is that experiments are very much like human endeavor. You have people involved. People have like flaws, right? When we communicate with each other, it's not that we understand each other automatically. We are, if you do an experiment, you have a domain scientist, you may have a statistician, you might have a technician. All these people need to kind of understand what the limitation of the experiment is and what they exactly want out of the experiment. So they have to come to a common understanding. And so part of the editable system is to really try to capture your user's intention and understanding of the experiment. And I'm hoping that, you know, this can be like a tool to help that. So as you saw in the first part of the takeaway messages, the relevant links are provided in this last slide. In particular, the last link here is actually to the link to the slides, which is emitanaka.org/slides/Toronto 2022. Thank you, everyone, for listening.
Thanks very much, Amy. That was amazing. I've never seen so much engagement in or praise in the chat. It's quite remarkable. We'll just have a few minutes of questions. If folks have questions, I'll just get started with our usual one. And then if folks have questions, they can just raise their hand and then I'll call on them. But our usual one is, do you have any books that you recommend, whether to do with experimental design or not?
So book-wise, I think this book called Telling Stories with Data is looking good, Rohan. Otherwise, if you want experiment design one, the one that I actually kind of learned is Rosemary Bailey's one, which I had in the slide itself as well. But I think that one is actually not easy for a lot of people. It gets a little bit mathematical as well. So it might not be something that a lot of people will like, but it gets quite good. I think Rosemary Bailey is one of the people who really did great stuff in experimental design, particularly for like in the agriculture field.
Well, that's excellent. Thank you very much. So I'll stop recording. Does anyone have any questions for Amy while we've got it?